Now we're going to look at the same Bell inequality from a different point of view. We're going to look at it from the point of view of a non-local game. So let's see how this works. It's supervised by something we'll call the house. And it goes like this. So we have Alice and Bob. And the house sends each of them one bit. So it sends the bit S to Alice and the bit T to Bob. So where S and T can be either 0 or 1. Then what Alice does is Alice sends a bit A back to the house, and Bob sends a bit B back to the house. And once the house sends the bits S and T to Alice and Bob, they cannot communicate. Now, what that means is that Alice has no idea what T is, and Bob has no idea what S is. Now, how do Alice and Bob win this game? So remember that we had Alice returns A equals 0 or 1. Bob returns B equals 0 or 1. And so how do they win? They win if ST equals 0, 0, 1, 0, or 1, 1, and A equals B. Or ST equals 0, 1, and A does not equal B. So those are the winning conditions. Now, what about, suppose they're playing the game classically, and we have no quantum mechanics in here. So there are this many possibilities to win if that have the condition A equals B. So we're going to assume that S and T are equally probable. So the probability of these three things is 3/4, 1/4 for this, 1/4 for this, 1/4 for this. And if that's, so the probability that they want to send A equals B is 3/4, and the probability that they want to send A not equal B is 1/4. So since they have no knowledge of S and T together, I mean, Alice knows S, Bob knows T, but Alice doesn't know T and Bob doesn't know S. The best they can do is simply send 0, 0 all the time. And if they do that, they will win in 3 out of 4 cases. So the best classical strategy and that means that they will win of 3/4. Now let's see what happens if we have some quantum mechanics involved. Suppose they share a finite max, and they can measure it. So what Alice is going to do, so Alice is going to measure A sub S. So in other words, if S is 0, she's going to measure A0. If S is 1, she's going to measure A1. And her result is A, is the bit she's going to send back to the house. Bob is going to do something very similar. Bob is going to measure BT, and his result is B, that he's going to send to the house. The winning probability here is in fact just equal to 1/4 times 2 plus square root of 2, and that is bigger than 3/4. This, in fact, is about equal to 0.85, and of course, this is 0.75. So by using this strategy, Alice and Bob can do better than they could with a classical strategy. Now let's just take a quick look and see where this comes from. So let me just take a look at a particular case and show that that in fact makes sense. So as an example, okay, suppose that ST equals 0, 0. So what's the probability that that should be an A equals B case? And so what's the probability that A is equal to B in that case? That is going to be equal to, well, it's A0 and B0. So it is going to be probability that A0 equals 0 and B0 equals 0, plus the probability that A0 equals 1 and B0 equals 1. Now remember we said that all those probabilities were the same for the case of phi max, and in fact this was simply equal to 1/8 times 2 plus square root of 2, and this one was also equal to 1/8 times 2 plus square root of 2. So if I add them up, that is simply equal to 1/4 times 2 plus square root of 2. Now the final thing is, how can we connect this back to the Bell inequality? Because we have, on the one hand, we had this Bell inequality that sum of a bunch of probabilities had to be less than 2 square root of 2. And now we're talking about winning probabilities of games being equal to 1/4 times 2 plus square root of 2. So is all this related? And the answer is that it is. So let's take a look at the overall probability of winning from the point of view of these probabilities. So the overall probability of winning is equal to, now, as I said, the S and T's are all equally probable, so the probability of any given S and T is simply 1/4, so that's going to be the first thing out here. And then I'm going to have a sum over M equals 0 to 1, and then I'm going to have a sum over S and T equals 0, 0, 1, 0, and 1, 1. So those are the ones for which the probabilities are supposed to be the same. And the probability then is going to be that AS equals M and BT equals M. So that covers the case where you want A and B to be the same. We have one other case, though, where you want them to be different. And so that's going to be plus sum over M equals 0 to 1. And then I'm going to have the probability that A0 equals M and B1 does not equal M. So what have we got here? So this is the one that corresponds to the case S and T equals 0, 1, where you want the A and the B to be different. Well, what have we got here? This is simply the sum of all 8 of our probabilities. And we know that that sum is in fact less than 2 square root of 2. So this is in fact less than or equal to, I can just replace this entire bracket by 2 square root of 2, and I just get 1/4 times 2 plus square root of 2. So you can see that in fact our Bell inequality is directly related to the overall probability of winning the game. So it's no surprise that we came up with this answer for the quantum probability. So this is 2 different ways of looking at a Bell inequality. One is a subset of probabilities has to be less than something, and that translates directly into looking at it in terms of a non-local game, where you can, using a quantum strategy, you have a higher probability of winning than you do with a classical strategy.